Hi. Recently, I installed a PV system with an inverter from a brand called Hoymiles. Hoymiles is quite popular in Thailand in microinverter space. It would be comparable to Enphase from the West. The energy production and the overall system works quite well, but the problem lies within the cloud platform. Hoymiles cloud platform only updates every 15 minutes, and that's way too long of an update. I want it to be more responsive, so I figure out what could be done. And today I'm going to share with you what I have made. Basically, it's a dashboard that updates around every 1 minute or so. And I'm going to guide you through as your navigator of how you could implement one yourself. Please note that this is not going to be a detailed guide that takes you through every steps, but more of an overview of how you could try to implement it yourself. Okay, without further ado, let's get to it. The first thing to talk about is how everything is connected together. On the left, we have the microinverter. The model I'm using is HMS-2000-4T. The microinverter is connected to DTU ProS over a sub-1G frequency. DTU ProS is connected to a small computer board. The model I'm using is Raspberry Pi 4B with 8 GB memory. And these two connects over a router via Wi-Fi. In my case, I have DTU ProS in a different subnet from Raspberry Pi. So you can see that the DTU ProS is in like .3.0/24 subnet, while the Raspberry Pi is in .5.0. In most cases, in normal home, you would have both of them in the same subnet. But for my cases, they just happen to be in a different subnet. And DTU ProS and Raspberry Pi has internet access over the router. So the router has default route to the internet. And this is how everything is connected together. Next, let's see how we can consume metrics from DTU ProS to the Raspberry Pi. To get metrics from DTU ProS, head over to the repository called Hoymiles-Wi-Fi over on GitHub. This repository provides you a Python package and also a command line interface or CLI to consume the data from the DTU ProS. So basically you can call Hoymiles-Wi-Fi, given it a host. This would be an IP address of your DTU ProS and a command to send to it. So the one that we are going to be using is the get real data new, and this one would give us the data needed for us to make our own dashboard. And you can also consume this as a library if you code in Python, but I haven't coded in Python for quite some time, so I'm going to use just the CLI interface. And yep, that's about it. You can skip to the next section, and from here I'm going to talk a little bit about the repository. So the repository hosts a protobuf file, so it seems like the DTU ProS has an RPC server that communicates with a protobuf. So in the protobuf directory, you can see a lot of proto files, and the one that we are going to use is the realDataNew.proto. So in here you can see the protobuf definition, and also you can see comments that is added by, I believe, the repository owner, so you can understand what each of these value means, and that's quite handy if you want to build your own dashboard. The proto file is compiled to a RPC client using protobuf compiler. If you head over to compile_proto.sh, you can see you can see that it invokes proto-c, which is a protobuf compiler, and specify you want a Python code out at this path. And so that should be it. Something more about the Hoymiles.py file. You can see that here we have the mappings and also the parsing of different values. So this could be useful if you want to look deeper into things. But yeah, that's about it. So in the next step, we are going to write some code. In this case, it's going to be a Node.js. It's going to be a JavaScript code to consume the data from the DTU ProRes. Before we jump into code, let's see the tools that we are going to use and also the data flow. First, we have dtu-consumer.mjs. This is our JavaScript file that will connect to the DTU ProRes to consume the metrics. It will write the data points to InfluxDB, which is a time series database. And then we have Grafana, which is going to provide us the dashboard user interface, which is going to query the data from InfluxDB. InfluxDB also have its own visualization tools, but I think it's subpar comparing to Grafana. So I'm going to use Grafana for this. Okay, now let's go into the dtu-consumer.mjs file. Let's begin by taking a look at the data that we are going to receive from the CLI tool that we discussed. Here I have two files, offline.json and online.json. This file represents the data when the inverter is online versus when the inverter is offline. And when it's online, it's going to have more fields than when it's offline. So I'm going to explore and point out some data points that might be interesting to you in the online.json file. So let's take a look at the root level metadata. Here it is an array because in a PV system, you could have multiple meters. In this case, I have only one meter and my meter is a single phase one. You can also get three-phase meter if your house is a three-phase system. And so here I only have phase A in the data, but if you own three-phase meter, you have phase A, phase B, and phase C. And so if you want to show some power, for example, you might want to add them up, or you could use phase total power, for example. The data in here, some of them has to be divided by 100 or 1,000, depends. You could refer to the DTO, not the DTO, the protobuf file in the Hoymiles.Wi-Fi repository to know what is value is about. And for example, voltage phase A, it's not possible to have like 22,000 volts. In fact, it is 228.90 volt, for example. So you need to divide by 100. And the current you have also, you should also divide by 100. Otherwise, you get like 300 amps, which doesn't make sense. Your house could blow up. The next thing is SGS data. This is the data from your inverter. So you can see that it shows active power and sometimes reactive power if your inverter puts in reactive power back into the system. And the current, the 1.8 amps at 228.8 volts back into the system. And the power factor, the temperature, which is 26.5, and so on, right? Okay, the next one is the PV data. This is data per PV panel. So you could use these two together to form a tuple to uniquely address a PV panel in your system. If you have two microinverters, you will get two different serial numbers, right? And you can use these two fields to form a tuple to identify the PV panel. And in each PV panel, you can see the voltage that it produced, which is 38.8 volt, 2.8 amps, and that comes to 1.109 watts. And that's about it. So I think this should cover most of the data that we need for our PV system dashboard. When it is offline, you can see that some fields will be missing. So you would need to account for this field when you write a consumer script to not crash if it cannot find these fields. Okay, given that I have talked about this, let's see the consumer.mjs file. First, I have a InfluxDB connection defined here. So you will need two things to connect to your InfluxDB instance. First is the URL, and the second one is the token. For the URL, mine is http://influxdb:8086. This is the port, and this is the DNS name that resolves to an IP address to InfluxDB database. The reason that I can use InfluxDB DNS name is because I deploy both consumer and the InfluxDB instance into the same Docker network. So here I have defined the InfluxDB, and here I have the consumer running. So it can reference this service name, and it will resolve to an IP address of the container. Regarding the token, you can create a new token in InfluxDB web user interface. So you need to log into, in this case, localhost at port 8086, and put in these two username and password, this credential, and you will get into the user interface, and then you can create your own token. And then you just need to put your token here. And I don't mind showing you this token because this is the token that's local to my InfluxDB instance on my local machine, and you don't access my local machine. Okay, the next thing is that we need to get the right API in order to write data points to InfluxDB. And I can do that simply by call getWriteAPI function on InfluxDB instance that I have created. And now I have the right API. This section is just a loop that runs itself every 1 minute. 1 minute without S. Okay, and then we have a consume function that gets called every 1 minute. In this function, I execute this command in a shell, and I observe the outcomes. If I received an error, I just do nothing. If I receive something from standard error, I also do nothing apart from logging the error out. And if I get a standard out, I just parse it, because standard out comes out like this, and I pass it to make it a JavaScript object so that I can access all the fields. And then I call this function passing in the parsed JSON data. And this function calls little small functions that extract the data from this data shape and send it to InfluxDB. So let's take a look at something simple first. So here we have send meter grid voltage. So basically I'm trying to obtain, where is it? Voltage phase A, this one, from the data. So here I destruct meter, the first meter from meter data, right? So I get this object, and then I try to destruct this one here. And then if I can extract the value from the object, then I send it over to InfluxDB. So I set the measurement name, and I give it a field called value, and passing in the value divided by 100. The timestamp I chose was from the data over here, so that every data point that's sent together shares the same timestamp. So it is easier to work with in the dashboard. A more complex one would be the PV module. So here I have to construct a measurement name from the inverter serial number and also a port number. So these two, as mentioned earlier, it will allows you to uniquely identify or address a PV panel in your system. So that's it. And I think that covers everything about the consumer script. You can write it in your favorite language if it's not JavaScript. So good luck. Then the next thing that I'm going to walk you through is the setup of the Grafana dashboard. To consume data from InfluxDB over to Grafana, you have two choices. The first one is using a Flux query language, and the second one is InfluxQL query language. Personally, I use Flux because I didn't know that Flux is now in maintenance mode. But as you start anew, I think you should use InfluxQL because Flux is not going to get any more new features. It still have security patches and critical bug fixes, but yeah, I think it's better to go with InfluxQL. But in this video, as I started with Flux, the example that I show later on will be in Flux. And welcome to my dashboard. I'm going to guide you through all the widgets that I have on my dashboard and trying to convince you why you should also have them. Okay, the first one is last updated at. This is a timestamp when of the data shown on the dashboard. And if the timestamp is, let's say, older than 2 minutes, I know that there's probably something wrong with the consumer script or the system as a whole. So I can go and investigate and fix the issue. The next line is consumption, which is the amount of power that I consume overall, and it splits into from grid and from PV system. So here you can see that I am currently using 462 watt, and I am using 30 watt from the grid and 471 watt from the PV system. Grid voltage, yes, it's a voltage of the grid. And phase A power. Power can be negative or positive depending on whether we are consuming power from the grid or we are actually producing power back into the grid. And we are now consuming 30 watt of power. Here is the grid voltage over time. So if it fluctuates a lot, that's not a good sign. So we can probably ring the utility grid company to help and investigate. Phase A power is the phase A power over time. And now I'm having trouble with this because my smart meter isn't working properly. As you can see, we have the data point here and then somehow another one here. It is missing a lot of data points. I don't know why, and I have to investigate it later on. And inverter production, this is the amount of power produced by the whole PV system per inverter. And I only have one inverter, so this is for my whole system. Next is the power limit. In Thailand, we are prohibited to produce power back into the grid unless we form a proper contract to sell electricity back to the grid. So we have to implement a system where we should limit the amount of PV system production to be in line with the consumption that we are actually using, so that we don't produce more than we use, and thus we don't produce power back into the grid. And this one is a power production by PV, so by PV panel. So we have 4 panels here, and this show the production of each panel. And when the lines are like apart from, doesn't like stay on top or close to other lines, that probably means something covers or something shades the PV panel, so I can go and pick it out. So this is quite useful. Next one is inverter power limit. This is related to the zero export function that I mentioned earlier, that we must not produce power back into the grid. This data is set by the PDU, not the PDU, DTU ProS to the microinverter. So the DTU ProS observes the power and then it computes the proper power limit to set to the microinverter. And as you can see, the power is broken now, so this value probably incorrect. The next one is inverter temperature, which is now 41. So we normally have a baseline temperature around 41 to 60 degrees Celsius, And if it goes above or below this, that's probably something wrong. Maybe the sensor broke or something actually happening close to the microinverter. So setting an alarm for temperature might be good, but I haven't done that. Next one is the power limit versus production. This shows the difference between the power limit set and the actual power produced by the PV system. For example, we set the power limit to around 2 kilowatt, but we can actually produce only like 438 watt due to the cloudy and almost about to rain situation here. And yeah, and that's about it. So if you find any of this useful, you can add it to yours. Okay, let's see some of the queries. Okay, let's go with inverter 1 production by PV panels. So I'm going to go to edit, and here is the query. So first I obtain a stream from a bucket called stats, and then I scope the data to be within this range, and the v.time range start and time range stop will be substituted by the value from the control here. So start will be this value and stop will be this value. And then I'm just filtering for the measurement that equals to each of the PV panels. So this will give us 4 tables. So if we switch to the table view, we can see that we have 4 tables here. And when we have multiple tables with the same columns that are time and value, we are going to get a graph like this in a time series graph. So we can observe the value over time. So the y-axis is the wattage and the x-axis is the time. So you can get the graph like this. Let's go to something more fun. It seems the power is healing itself. So nice. Okay, I don't have to do anything. Maybe consumption. So consumption has some calculations in it, and I'm not entirely sure if this is correct, but I hope it is, and I think it is. But if it's not, please let me know. Since I'm using Flux, it has a concept of functions. I define here 2 functions, from grid and to grid. As we know that power can be negative or positive depending on whether we are consuming or producing the power from and back to the grid. So from grid, we'll check if the power is negative. If that's the case, we only get the magnitude of the power and disregard the direction of the power. And the same goes for to grid. If it's more than 0, then that is the power sending back to the grid, and otherwise it's 0. And the reason that I need to define these 2 functions because I need to do some calculation on line 16, and I want only the magnitude of it. I don't want the direction of the power. Okay, let's see the 2 tables which will be joined later on. The first table is meter power. This is the power that we talked about, and here I have modified the table to include 2 additional fields. First one is the from grid, and the second one is to grid, which invokes the corresponding functions. Right, and the inverter power, which is going to be positive always because inverter only produce power, it never consume. And I am just filtering by the measurement to get the power of the inverter. And now I join these 2 tables together on the time column. And if you remember that we use the timestamp from the measurement rather than like due date, the date when the data point is created, this allows us to join pretty easily. Otherwise, I would have to aggregate the data first and apply some aggregation function, and then I can join the table later on. which is troublesome, and this helps a lot to simplify things. And next is that we calculate a value and override the value field. I'm going to format this a little bit so we can see it easier. Okay, so we are operating on 3 values to get the final value that we show here. The first one is the value from the grid and to the grid, and I multiply it with 1000 because this value is in kilowatt and I want it to be in watt so that it is in the same unit as the power inverter power. So with they all in the same unit, I can calculate it normally. So here I have from grid plus the inverter power minus to grid. That will equals consumption. The train of thought is like this. Let's say in a scenario where we are producing power more than we use, right? From grid will be 0 because this function, right? Else 0. And we are left with these 2 values. It is the power that we produce minus the power that the meter measured and found that we send back to the grid. So this is the actual consumption. Right? Another one is the case where we are using less power. We are producing less power than we are consuming. So we are consuming more power than we can produce. Okay, in that case, we are going to have a positive value here, but a 0 here. So it basically just from grid plus whatever we produce. So I think that makes sense. Since this is addition, I think we can actually like merging this into just a meter value, meter power, without having to separate it into from grid and to grid. It might simplify things, but this makes more sense, I believe, to get the actual consumption. And then we just keep these 2 columns so that when the data arrives at Grafana, we only have these 2 columns, and that saves some bytes over the network. And then we get the last one to show here as a single stat. And that's about it. This is my dashboard, and yours may be different. Have fun exploring. Bye.